We worked on the calculation of earth pressures in the previous lecture. So we figured out how to understand the loading conditions that is needed for designing the earth retaining structures. In this lecture, we will see how to analyze and design earth retaining structures for stability. The objective is to help you guys know how to design earth retaining structures against sliding and overturning. For the goal, we will arrange this lecture into 4 parts. We will be first looking at the common earth retaining structures. Then we will see what types of failures or failure modes we could have for earth retaining structures. Next, we will be focusing on the analysis associated with 2 primary types of failures in earth retaining structures, that is sliding and overturning. Let's take a look at the common earth retaining structures. There are different types of earth retaining structures, temporary ones and permanent ones. Here we are focusing on the permanent earth retaining structures, primarily retaining walls. For retaining walls, one of the most common type is the gravity wall. So the gravity wall is just like a very big block of concrete or masonry. For this type of retaining wall, we take advantage of the gravity of the wall itself and use that to stabilize the soil on the backside of the retaining wall. Another type that we need to know about is cantilever retaining wall. So we will leave some space between the 2 types of walls because we'll add something between them. A typical cantilever retaining wall looks like this. It has something called a stem. Here shows the cross section. So this thing is called the stem, and the backfill and the soil is on this side. So this is the back. And here we call it the heel. What about this point? How would you call it? It's toe, right? And this is gravity and the cantilever. And you can see that cantilever walls, they're much thinner. And in order to ensure we won't have failures in the structure, usually we add reinforcing rebars in it. And because of the very unique shape of the cantilever retaining wall, the mechanisms underlying the cantilever wall is much different from that of gravity wall. The gravity wall, we use the gravity only, but for the cantilever wall, we also utilize the weight of the soil behind the back of the wall. So this type. So we kind of add the weight of the soil in this area to the weight of the retaining wall to help stabilize the soil. here. We also have something between these two types. It's called semi-gravity. So it's thinner or slenderer than the gravity one, but much thicker than the cantilever was. And for this one, we also have reinforcing rebars in it. And in this course, we will be introducing the theories for gravity wall and cantilever wall. So here, add a little bit of notes here. We use this soil weight in addition to that of the wall to stabilize the system. And regarding the dimensions of different types of walls, especially for the cantilever wall, we have something called proportioning. That is, for different dimensions, we have typical dimensions include the thickness at the top of the stem and the width of the bottom of the wall. Actually, it's the base, the speed, and also height, as well as other things such as the angle, the inclination angle of the wall. And these things all belongs to proportioning. For proportioning, there are some general guidelines. For example, for the T, the thickness of the top of the stem, you need to be greater than 1 inch to avoid difficulties for casting concrete, because we poured concrete from there. You can get such information on page 652 in your textbook. That is for proportioning. So these are the types of retaining walls that you need to know about. Then let's take a look at the stability of retaining walls. So the retaining walls or other types of earth retaining structures, they can fail in different ways. So we call these different types of failures or different failure modes. There are 4 that we need to know about. The first one is sliding. So if I use a cantilever wall as an example, the original position of the wall is here. But if sliding occurs, the wall will be pushed by the soil to move to its left or to the direction that is away from the soil body. So this is sliding. This is similar to the sliding resistance that we discussed in shallow foundation. Sliding is caused by the force along the horizontal direction. And overturning is the second mode So for this one, the original position of the wall is here. And if overturning happens, it will rotate. And in general, we assume that you rotate about the toe of the wall. So toe is here. We just talked about that. And this one is caused by the overturning moment. So it's not a force, it's an overturning moment. And the toe, we usually call it O, point O. And this is the overturning failure mode. The third type of failure is actually what we discussed a lot when we are learning the design theory for shallow foundation. We can also view this wall as something that's analogous to shallow foundation. So if that's the case, we're going to have the bearing pressure distribution like this. Does this distribution of bearing pressure ring a bell? It looks like the eccentrically loaded shallow foundation, right? So actually, the failure mode is exactly the same. That's the bearing capacity. So the soil below the wall cannot sustain it. And for this one, it is similar to eccentrically loaded shallow foundation. And because of that, we can use the theory that we introduced for eccentrically loaded shallow foundation for analyzing this type of failure and to calculate the bearing capacity. The last type of failure is related to the last major topic of this course. That is slope stability. You can see that we have soil on the backside of the retaining wall. That soil body can also have slope stability issues. So if that happens, we may have a slip surface like this. And this type of failure is called a deep shear failure. And it's the one for slope stability. As mentioned, we will be talking about sliding and overturning. And for bearing capacity, you can refer to what we introduced for shallow foundation. And for the last one, you'll get some information when we will have the last lecture for slope stability. Next, let's see how we can analyze the stability with respect to sliding. Let's recall the allowable stress design first, and we're gonna use the force version of it. So for the force version of the allowable stress design, we have the equation: the actual safety factor equals Q is total resistance force, and F is the sliding force here. So let's write it down. This is the resistance but it has the unit of a force. Or we count capacity, same thing. And F, this is a sliding force. Here, it's the force that can fail the building. And this one needs to be greater than or equal to the design safety factor. And we will see that for different types of retaining walls, we will have slightly different equations for calculating the actual safety factor. So we will be introducing the equations that we will need for analyzing the sliding resistance of gravity wall and the cantilever wall side by side. So on the left, I will do gravity wall. And on the right, I'm going to do cantilever. For gravity wall, let me draw a schematic first. We will start with a simple case. So we have a vertical back for this wall, inclined backfill, and the angle is alpha. For this one, we have gravity. So in order to get this actual design safety factor, we need to figure out the Q and F. So let's take a look at the static equilibrium of this wall. To do that, we need to find out all the forces, and the first one is the weight. And between the wall and the soil below it, we know that we're gonna have friction. Let's call it F mu, that's the frictional force. And we know the soil on the back of the wall will also apply force on it, and that is F. And if we think about the situation for sliding, it usually happens when soil pushes the wall away. So the wall moves away from the soil. And if that's the condition, so what type of earth pressure we would have? If wall moves away from soil, in that case, soil pushes against the wall actively, right? So we have active earth pressure. Accordingly, this force is going to be Fa, so the active force. That's the resultant of the active earth pressure. And it has an angle because we have friction between the soil and the back of the wall, so it's not horizontal. And we call this angle alpha F, so that's the angle of the force. But this one depends on which theory we have. If we are using the Rankin's earth pressure theory, then alpha F equals alpha. That is the inclination angle of the backfill. This is for Rankin. If we are using Coulomb's theory, then this angle is 90 degrees minus beta. Remember, this is beta. Here we do it in a simple way. We draw a vertical one, but this one can also take care of non-vertical angles. Plus delta prime. Delta prime is the friction angle between the back of the wall and the soil next to it. So we know that for any force, we need three things. We need the magnitude, we need the direction, and we also need the position. That is the point of action. In this case, we know the magnitude is Fa. That can be obtained using the earth pressure theory. For the angle, this is what we get for alpha F. For position, no matter we're using Rankine's theory or Coulomb's theory, the distance between the point of action and the bottom will be 1/3 of h. Then let's take a look how to get the Q and F. Before we get a Q, let's take a look. Actually, there's another force, that is the normal force. This normal force will cancel out with the normal force from weight and also from the vertical component of Fa. So F mu, how to calculate F mu? We know F mu equals the product of the normal force and the friction coefficient. Let's say this delta prime is the friction angle between the wall and the backfill. And sometimes we will use a different friction angle between the bottom of the wall and the saw below it. That's called delta 2. But in many cases, people use the same angle for these two friction angles. Let's calculate the total vertical force first. That would be W is vertical. And we also have the vertical component of Fa. So that is Fa times, here out sine alpha F. Then this is the normal force. Need to multiply the friction coefficient. That is the tangent of delta 2 prime, because we're talking about the friction at the bottom. And then we can get the actual safety factor. It's Q over F. And the Q in this case, that's the resisting force. That's the force help stabilize the system. That's the friction in this case. So friction try to resist the leftward movement of the wall. So try to push the wall back to its original position to help stabilize the earth behind it. F is the force that moves the wall to the left. So in this case, that's the horizontal component of Fa. That's Fa times cosine alpha F. Then we substitute the equation for Fu into this equation. We will get the final equation for calculating the actual safety factor. And in this equation, we know that Fa comes from the previous lecture for calculating the earth pressures. And it depends on which earth pressure theory that you use. You may get different values for Fa. So this is for gravity wall. Then let's take a look at the cantilever wall. For cantilever wall, we know there's one major difference is that now we try to utilize the weight of the soil in this region. So this is a line that we get by drawing a line starting from the heel and then go vertically. That will intersect with the surface of the backfill. For this wall, let's take a look at its mechanical or static equilibrium. We're going to have weight W And we also need to consider the weight of this soil body. In this case, as mentioned, we will have active earth pressure. So this would be the active zone because the soil moves actively to push the walls away from its original position. That is WA. Then sometimes, we also have soil in front of the wall. That means we also have weight. That's the passive zone. Because soil in this region, they will move passively because the wall moves against it. And we may also have FP, that's the passive pressure, but these two things, they're usually negligible, so we do not consider them. And then between this active soil body zone and the soil to the right of it, we also have the force. Because the soil in the active zone moves away from its original position actively, then the soil to the next of it will also move in the active mode. So we will have active pressure, and this is a resultant of the active pressure. Then for the active pressure, we can get the magnitude of it using one of the earth pressure theory. For the direction, we also use alpha F. And alpha F is different from the gravity law. It's alpha for ranking, and it's delta prime for Coulomb. Regarding the position of this FA, the point of action here, the distance from this point and the toe here, this is 1/3 of H prime. So be careful, here's not H anymore. And H prime is the distance from here, from the heel to this point. So let me draw it here. So from here to here, this is H prime. So that's not the height of the wall. We can use the same way that we adopted for getting the actual safety factors for the cantilever wall. Let's try to get the equation for the friction force first. For this one, for the friction force, is the product of the normal force and the tangent of the friction angle. So for the normal force, let's see which force act downward. So we have W. We also have WA and the vertical component of FA. So that is FA times sine alpha F. Then the summation of all these vertical force times the friction coefficient. That is the tangent of the friction angle. So this is the F mu is the resisting force. So for the actual safety factor, it's also Q over F. F mu over FA times cosine alpha. And we plug in the equation for F mu. We'll get W plus WA plus FA sine alpha F. This quantity times the tangent of delta 2 prime. Then denominator is FA times cosine alpha F. So this is how to calculate the stability of the gravity retaining wall and the cantilever wall against sliding. Next, let's work on the overturning of these two types of retaining walls. We will also be working on these two types of walls side by side. On the left, let's do the gravity wall. And on the right, we're going to have the cantilever. So we're going to draw the retaining wall here. For simplicity, we will use a vertical back. As long as you know how to do a wall with a vertical back, you will be able to know how to deal with the wall with the inclined back. So for this one, let me mark dimensions. Here's the T. Here, this is B. And we have the angle of inclination of the backfill, alpha. And we know we will have the FA acting at this point, which is 1/3 of H from the bottom of the wall. And the angle of this force is alpha F. This is what we learned in part 3 of this lecture. And the distance from this point to the bottom is 1/3 of H. Now we need to modify first, before we get into the equations, we need to modify the equations for the safety factors a little bit. So let me do it here. SF actual, this is for both the gravity wall and the cantilever wall, equals, now because we're talking about overturning, so we are talking about the moment instead of force. So let's use M. So it's going to be MQ over MF. The meaning of F, M over Q, that's the anti-overturning moment. And we know it is the resistance. The MF is the overturning moment. And when we are calculating this moment, for any moment, we need to talk about the point around which the moment will be calculated. So here, that's usually the moment were calculated about the toe. But of course, you can use any other point. But toe will simplify your equations significantly. So try to use this one. It's point O. It's the point about which we will calculate all the moments. So we need to get the M sub Q and M sub F. Let's take a look at how to do M sub Q. M sub Q is the anti-overturning moment. In this case, when we say overturning, that's the soil overturn. So this is overturn. And you can see that the overturning direction is counterclockwise in this case because the soil is on the right-hand side. And the anti-overturning direction is clockwise. So we need to figure out which force will generate a anti-clockwise moment around point B. So that would be contributing to the anti-overturning moment. And of course, we will have weight But in order to simply calculate the weight, here we're going to use this technique. We will divide the region of the wall into multiple regions with simple shapes, either triangle or rectangle. Because for triangle and a rectangle, we know the centroid of it. If you do a trapezoid directly, it's difficult. And sometimes if we have inclined back, that will make it more challenging. If it's inclined, you're going to need to generate another triangle here. So in this case, the back is vertical. We only have two. One is triangle, one is rectangle. And we know that for the rectangle, the centroid is right at the center. So let's call it this one 2, so it's W2. And the triangle is 1, so it's going to be W1. That's the weight of region 1 and the weight of region 2. We have F, A. We also have friction, but you can notice that for friction, the line of action of the friction pass through point O directly. So that means when we are calculating that moment, we don't need to consider this force. It has no arm. That's one of the major reasons that we choose point O as the point for calculating the moments. So MQ, that should be the counterclockwise moment, and we know W's different weights will be contributing to this moment. So the W1, let's take a look at W1. W1, we know it is the distance from this point to point O will be 2/3 of this distance, and this distance here is B minus T. So that means the distance from the centroid of the triangle to point O is 2/3 of B minus T. Then plus W2. For W2 is in the center, so the distance from W2 to O, that's from here to this line, will be B minus 1/2 of T. So this is 1/2 of T. T divided by 2. Then F can also contribute to the anti-clockwise or the anti-overturning moment. But if we try to get the moment caused by FA directly, that would be challenging. So we split it into two components, the vertical component and the horizontal component. And if you take a look, you will find that the horizontal component will generate a anti-overturning moment, and while the vertical one will generate a clockwise overturning. And here we are talking about anti-overturning. So which one we should have? Let's put it here. Clockwise here is for anti-overturning. I may give you guys some wrong information, so I want to make a correction here. Clockwise, anti-overturning. So here we talk about the clockwise. We know the vertical one will generate a clockwise moment. That's the overturning moment. So the vertical one is FA times sine alpha F times, and the arm here is from this point to here, so it should be B. MF, if we take a look at all the forces, you will find that only the horizontal component of FA can generate a counterclockwise moment. That's the overturning moment. So the horizontal component of A is FA times cosine alpha F. And the arm of this force is just 1/3 of H. Then put everything together, we can get the actual safety as MQ over MF. So you guys can copy the equations here. This is for the gravity wall. Then let's take a look at the cantilever wall. So for cantilever wall, we also overlook the weight of the passive zone and also the passive force. We overlook this one. We have T here and B here. And we have the weight of the active zone WA. Then have FA, and this point is 1/3 of H prime from the bottom of the wall. We want to figure out moments around point O. If we choose point O, then we don't need to consider the friction force because it passed through O, so it will cause no moment about O. Then let's see how to do MQ first. We use same equation MQ over MF for the actual safety factor. For MQ, we need to do it in a similar way like what we did for the gravity wall. So we need to divide the cross section of this cantilever wall into multiple regions, and each region would have a basic shape, geometry, either a triangle or a rectangle, because only for these basic geometries we know the centroid of them. So here we will not do that, but I will write it in a general way. Let's say that we divide the cross section of the wall into n regions. So divide the cross section into n regions. And for each region, we know the weight of it is Wi, and we also know L. L is the distance from the centroid of region I to point O. This is the distance from the centroid of region I to point O. We still have the weight of the active soil zone. So that's WA times LA. So LA can also be obtained based on the geometric relationships. We know that it should be here at the center of this one. So here from here should be at the center. And the distance from here to here can be calculated. Depends on the geometry. Last one is the FA, and we know the vertical component of A creates a clockwise or anti-overturning moment. So FA times sine alpha f, that's the vertical component of it, then times the arm of it. Arm is just b. mf only has one contributor, that's the horizontal component of fa. Fa times cosine alpha f is the horizontal component of fa. Then the arm of it is h prime divided by 3. So with the equation for mq and mf, then we can get the actual safety factor as mq divided by mf.
I think I'm falling for you.